So how are you all doing this morning? Yes, I understand. That is difficult. Let's see. Okay. Good morning. So let's talk some more about these. Let's make sure that we all actually can understand what they're talking about, because the purpose of this chapter 1 is so that when you see these symbols, that you understand in your brain what it's talking about in terms of the thinking process. So sometimes people call this mathematical thinking or mathematical reasoning. So these arguments, or whatever they're called, they are basically a list of things that are assumed to be facts. So there's two facts above the blue line, and then there's a third thing below the blue line that's not, you don't know for sure if it's a fact, and you have to decide whether you know it's true or not based on the facts that you do know are true above it. So, for example, here's an real world example. If somebody can lift 300 pounds of weight, and then would you know that they could lift 200 pounds of weight? Like if they could lift a barbell that had 300 pounds of weight on it, would they be able to lift one that had 200 pounds of weight on it? And yeah, assuming it's not a trick question or anything, which I'm not meaning for it to be yes, the answer would be yes. So that's just an example of that. Like the P at the top, let me see if I can get a pencil thing with you real quick. Okay, good. So the P, oops. Oh, there we go. Okay. The P at the top, that's like knowing for sure that you actually did see them weigh 300 pounds. And then the second one is just a general fact. It's not what they did, but you know that if somebody could lift 300 pounds, then they could at least lift 200 pounds, right? So the first thing would imply the second thing. So the first part is what you actually saw. Let's say you did see them lift 300 pounds. The next thing is just an inference that if somebody could lift 300, that they could lift 200. So if you actually did see them lift 300, and you really saw it with your own eyes, and you also know that if they could lift 300, that would imply that anybody who could lift 300 could lift 200, then therefore you know that that person can lift 200, right? So that's basically what that means. Let's try to think of another example of that exact same thing. So would one of you be willing to think of an example where there's something that implies something? So give me an example of something that implies something else, that if you know one thing happens, then you know something else happens too.
You don't come to class today, then you miss out.
Yeah, if you don't come to class today, then you miss out. So let me write that down. So if you don't, I'll put the exclamation point, which can also mean not as well. If you don't go to class, then I'll draw an arrow, then you miss out on whatever happens in class. So now that doesn't mean that I know that you missed out, right? Because I didn't necessarily know if you didn't come to class or not. So is that enough to prove that somebody missed out? No, because I don't know actually if they did miss class. So let's say if you know that it's true that if you didn't go to class that you'll miss out for sure. And then let's say if you also know that Bill did not go to class. Okay, what can you conclude from that? From those two given facts? What argument can you conclude? What's a valid conclusion from that?
Bill missed out.
Yeah, exactly. Bill missed out. Because you know that for Bill, he didn't go to class. And you know that also in general that if somebody didn't go to class, that they'll miss out. So since he didn't go to class, he missed out. Does that make sense? So when you see that, when you see all this stuff like this, see that little thing behind there? That's a little bit hard to understand, but as you learn the symbology, as you learn these symbols better, you'll start to realize that's exactly what that's saying. So P, this you didn't go to class, and the symbol and, you know that if you don't go to class, that you'll miss out. That's the P implies Q, therefore Q, right? Okay, so then let's go to the next one. Let's try to think of a real example of that one as well. So what's the next one saying? Let's try to use that same example. So, do you want me to, well, we could use one of the two. Do you want me to use the example of the weight? Or do you want me to use the example of the class? Which one would be easier for you to understand? How about the weight? I think the weight's a little bit more concrete. So you know the second one is saying if P then Q, right? So if you can lift 300, that's what we talked about last time. If you can lift 300, then we know that you can lift 200, right? That's a valid implication, right? Unless there's a trick question like there's like thorns on the weight or something like that. But assuming everything's fair and it's just the same kind of weight and the same kind of everything, then it's true that if you can lift 300, then you can lift 200. So now what is it? What's the top one say? What's the top one say? Does it say not P or not Q? It says not Q, right? So since the Q, which one does Q represent? Right. So the antecedent, they call that the part that's before the implication. The consequent is the part after the implications, the arrow symbol. So we know that the Q part is not true, so they cannot lift 200, right? So we know that if you can't lift 300, that's just a general fact that then you can lift 200. But for this particular person, let's just say Bill cannot lift 200 pounds. Bill cannot lift 200 pounds. So what valid conclusion can you conclude, or what argument can you make based off of those two facts? If Bill cannot lift 200 pounds, I mean, right, then he cannot lift 300 either. Because if he could lift 300, then he could lift 200, right? But this is a little bit more complicated of reasoning, though. It's not direct reasoning. It's like a little bit more complicated than that. You cannot lift 300 either, right? So, does that make sense to everybody? I actually see a lot of people making mistakes in that second kind of argument, though. Like, you have to be careful. If you know the P implies Q and you know that you don't have Q, then remember you don't have P either. So it's a little bit confusing sometimes. If it's not something to do with if it's something with like weights, it's very clear to understand. But if it's something that's like more abstract, it's kind of hard to understand. Okay, what about the next one? What about the third argument? P implies Q and Q implies R, then P implies R. So let's think about that. Let's think about weights again. So what could P be? What is a amount of weight that you could lift up that would imply that you could lift up another amount of weight? So if you can lift, let's just say the P represents lifting 500 pounds. If you can lift 500, that would imply what? You could lift 400, right? And so now the next one is still Q. So we have to start with the same amount as the end of the last sentence because it says P implies Q and then it says Q implies R. So, yeah, if you lift 400, then you could lift 300, right? So they're getting easier and easier as you go down the thing. So what's the argument that it makes at the bottom? It says P, the very first one, implies the very last one, right? If one thing implies another thing, and the other thing implies something else, it's basically saying that's getting easier and easier and easier. Then if you can do the most, then you can also do the least, right? So if you can do the strongest amount of weight, you could also do the easiest amount of weight. So the valid argument for this would be that if you can lift 500, that would imply that you could lift 300, right? Does that make sense? So anybody who can lift 500 can lift 300. Even if the only facts you know are that somebody who can lift 500 can lift 400, and if you know that somebody who can lift 400 can lift 300, then you still know that it's also true that somebody that can lift 500 can lift 300. Okay, let's try to visualize the next one. If for some reason some of these things are not, and I'm just gonna clear all of the things at once. Okay, what about the fourth row? What's an example of that? So we can't use necessarily weights because this is two things that you can do, one thing or the other thing. So what could we say? By the way, which symbol is that? The one that's like this? Or, right. So that says P or Q, right? So somebody give me an example of P or Q. So, yep, so let's say somebody, Bill can ride a bike or walk. Now remember, in logic, that's not saying that he can't do both. You'd still say in logic that Bill can ride a bike or walk, and he could possibly do both. But you don't know if he can do both, but he might be able to do both. You do know for sure that he can do at least one or the other, right? So Bill can ride a bike or walk. Now the thing is, what's confusing about this is you don't know if he can ride a bike, you don't know if he can walk, and you don't know if he can do both. But all you know is that he can do at least one of them. He could do both of them, and you don't know which one he can do, but he can do at least one of them, right? So you don't actually know very much because from that one sentence, you can't say whether he can ride a bike, and you can't say for sure whether he can walk. All you know is that he can at least do one or the other, and he could even do both. So an or statement is not very, it's a little bit vague, but if you add some more information to that sentence, then you can get a more definite conclusion though. So what does it mean when it says not P? So in this case, the P is the first part. Bill can ride a bike. And the second part is can walk. So if it says not P, what's that talking about? You cannot ride a bike, yeah, because the P is the part that comes first. So we know that Bill can ride a bike or walk, but we also know we saw him or whatever we know, like let's say we're his parents or something like that. We know that he cannot ride a bike, right? But we know that he can do at least one or the other, but we know he can't do the first one. So what can we conclude? He has to be able to do the other one though, because if he can't do the other one, then he's not able to do one or the other. So if you know Bill can ride a bike or walk, and you know that Bill cannot ride a bike, then you know what can he do? If he cannot ride a bike, but he can do at least one or the other, then what's the only thing left that you know for sure that he can do? Yep, Bill can walk, right? True. So that's basically the argument that if you know somebody did at least one of two things, but you can rule out one of the things that he did not do, then they must have done the other thing, right? Okay, let me start about that. You ready to go to the next one? The next one is actually not necessarily a very useful argument. It's actually more of a way of confusing people to give them like doubt a little bit. So let's see how that one works. Okay, so let me just clear that. So notice that we're actually making something simpler become more complicated of adding stuff onto the argument. So let's say how many facts are there listed above this argument? Just one, right? So it could be anything. So think of something that could be true about Bill. What? Bill could walk. Right. Yeah, but let's say Bill could walk. No, and it could be Bill could walk, but okay, let's think of something good or something bad. Think of something good first, actually.
He has the ability to walk.
Yeah, but let's think of something good, like Bill's a hero. What could Bill do that's a hero? What? Bill saved a cat. Okay, that's good. Yeah, Bill saved a cat. Okay, so that's something good. That's the only thing you know is Bill saved a cat. Now, if you didn't like Bill, you could say a true statement. You could add on something totally unrelated to that. So what's something that's bad that Bill could do?
Bill let the cat die.
Yeah, so we could say, therefore, if we know that Bill saved the cat, and that's really what we know, but we don't want people to like Bill, so we could say, well, Bill saved a cat, or, or let the cat die. So now if you put that in the news, it's true, but you actually know that he didn't let the cat die at all. You know that he saved a cat. But that is still true though, because he did for sure do one or the other, right? You're not lying. So that's actually a valid argument, but that's kind of a mean argument though, right? But it's still valid though. So like if you're a lawyer, you can, if you know somebody did something, you go to court, you can provide evidence that like proves that they did one thing or the other thing, and you're not going to tell the court like that you really know he just did one thing, but if there's something bad that they think that he might have done, you could just leave that in there. Like you could prove that he was like at the side of a crime, but maybe you really know that he was actually just like helping, help, like donate some food and water or something like that. But if you don't tell what he was actually doing though, and you prove that he was there at the side of the crime, then people might think, oh well, maybe he did the crime instead of the good thing. Does that make sense? So if you know one thing is true, you can just add on to that. That's called addition. But you have to use the or symbol. So anything you want to in the whole world, you could say add, you could or. Like you could say Bill went to the moon. You could say Bill saved a cat or Bill went to the moon. That's true because in an or statement, you can add things that are false and keep adding them to the or statement. And the overall or statement is still true as a whole, as long as at least one of the things is true, right? Now let's talk about simplification. Sorry, whoops. Simplification. So this is where you start with something bigger and you lower it down. So this is like what you might have a mean supervisor at work. This is what your supervisor might do. Like if you did lots of things during the year, like lots of hard projects, your supervisor doesn't like you, they might simplify it down to just say like you did one thing. So let's say Bill, Bill saved the university. No, actually, let me write it like this. Sorry. Bill. Okay, so Bill. Bill went to his office one day. That's P. So that's easy to do, right? Everybody has to go to your office one day, at least. Bill went to his office one day, and then Q could be, and then we'll say, and the second thing is Bill worked. Well, I'm just gonna keep it simple. Say Bill saved the university. The university. So maybe Bill like had to work like 80 hours a week and like maybe had to like sacrifice all of his mental health and like finally maybe the university was about to go bankrupt and Bill talked to everybody, like found some donors and like saved the whole university. So how could we simplify that? How could we simplify it from Bill did this and Bill did that? What's a valid statement that we can make from that?
The office saves.
We could leave off the second part, right? So if Bill did this and Bill did that, therefore it's true that Bill did the first thing. We're not lying, right? But that's really mean though. If you cut off part of what's true, that's called simplification. It's still true. You're not lying. Like Bill did go to his office one day. Like, well, what did Bill do this year? Well, Bill went to his office one day. That doesn't sound like Bill is a very good worker, right? That's why if you go to a court, you have to swear to tell the truth, the whole truth, and nothing but the truth. So this is the truth, but that's not the whole truth, right? But of course, in logic, as long as it's true, it's still true that it's not false. So it doesn't have to be the whole truth to still be a valid logical argument. So we're learning about some of the dirty arguments in logic now. They're still true, but they're not very nice though. So what about conjunction? What does that mean? By the way, have you ever heard of a conjunction before in algebra? Remember we learned about conjunctions and disjunctions in algebra? So actually the word, the symbol and is called a conjunction. And the symbol or is also sometimes called a disjunction. Okay, so conjunction. Let's say I know two facts. Let's say that I saw Bill one day and Bill was saving a cat. So first let me clear the screen. So I'm gonna circle that one. That's what I'm thinking about. So Bill saved a cat. And then let's say another day I saw Bill and Bill saved the university too. Saved a university as well. So then what argument could you make? If you included everything that Bill did, what argument could you make? You could say that Bill saved a cat, and you could say that Bill saved the university, right? So Bill saved a cat, and Bill saved a university. A university. Okay, that's cool. All right, now this last one's kind of hard to understand though. So let's try to boil it down into something simpler. So first of all, does this last one make sense? You know, two separate facts, then you can also say that it's true if you said both facts together, right? So if one day you saw Bill save a cat, and if one other day you saw Bill save a university, then you could say truly that Bill saved a cat and Bill saved a university. Then the very last one, this is called resolution. This is a little harder to understand. So let's go back to the idea of walking. So what are three activities you could do? Like walking, what else?
Rolling.
Walking, running, and riding a bike. Okay, so let's say that you know that Bill can walk. No, actually, no, we don't know that Bill can walk. This is a hypothetical. So remember, absolute facts are just written as just a letter by themselves. Logical statements are the ones that are written like logical things between them. So we don't know for sure that Bill can walk. What we know is that Bill can walk or okay, should I say run or should I say ride a bike for the next one? Run.
Nice tier of ability.
Yeah, I guess we could say that. I don't want to make something that contradicts the next part of it though. But I don't think it will. So Bill can walk or Bill can run, right? So P is the walking and Q is the running. That's one fact we know is that Bill can walk or run. And then the second thing we know is that Bill, so what's the opposite of P?
Sprinting.
Bill cannot walk, right? Bill cannot walk or Bill can ride a bike. Okay, so what valid argument can you make from that? So you know the Bill can walk or run, but you don't know which one he can do for sure. And then you know Bill cannot walk or Bill can't ride a bike. So it's a little bit complicated. In fact, this is one that might actually be easier to do if we just had the letters. We just crossed off the letters that could be or couldn't be. So
So it'd be determined by running and biking at the end.
so let's just play the devil's advocate and just assume that one of them's true. So let's say Bill can walk. In fact, let's say Bill can walk. So if Bill can walk, then what do we know about from the second one? If Bill really can walk, then it's not true that he cannot walk, But we know that it's true that he either cannot walk or that he can ride a bike, right? So if he can walk, then it's obviously not true that he cannot walk. So therefore, he must be able to ride a bike, right? So if he can walk, then we know that he can also ride a bike. So now let's take the opposite case. What if he cannot walk, though? What if he cannot walk? Well, if he cannot walk, then we know that we know that he either can walk or he can run, right? So if he cannot walk, then it can't be true that he can't walk. So therefore, it must be able to run, right? So we know that he's able to either run or ride a bike. So therefore, he's able to. Now, this was not a good example to walk and run, because really, if you can run, that really implies that you can walk. So those are not really two independent things. So that was a bad example to use. But we know logically that he can either run or that he can ride a bike. Now, of course, we actually know from common sense that he couldn't run necessarily if he couldn't walk, but we don't know if he can walk or if he can't walk. So basically, if he can walk or run, if he cannot walk or he can ride a bike, then therefore he's either able to run or ride a bike. So if he is not able, if he can walk, you know for sure he can ride a bike, right? Because of those two different things. Let's think of a better example. That's a bad example because running implies walking. So what's something that does not imply something else? What's something that does not imply something else? What about like playing the violin, let's say. So Bill can play violin, or okay, what's another thing besides the violin? Guitar. And now this time it's not true that being able to play one would imply the other, right? So Bill can play the violin or guitar. And what would the second sentence look like? It'd start with saying you cannot play the guitar, right? So Bill. Oh yeah, violin, you're right. Bill cannot play violin, you're right. Because it's not P. Or now it's the third instrument this time because it's P, Q, and then R. So Bill cannot play violin, or he can play what else? Or he can play trumpet. All right, perfect. So based on that, which one of at least two instruments do you know he can play at least one of which two instruments? Well, so once again, let's just play the devil's advocate. No matter what, it's either true that he can play the violin or not, right? So let's consider both options. If it just so happens to be that he really can play the violin, then you know that he either cannot play the violin or he can play the trumpet, right? So if he can play the violin, then it's not true that he cannot play the violin, right? So therefore, since he has to either do this or this, therefore he has to be able to do that though. So if he can play the violin, then he has to be able to play the trumpet, right? So if he can play the violin, he has to be able to play the trumpet, right? But what if he cannot play the violin though? What if he doesn't play the violin? Well, if he doesn't play the violin, then if he does not play the violin, then this is not true, right? So if this is not true, it says this is true or this is true. So if this isn't true, then therefore this has to be true because one of them has to be true at least. So we know that for sure that he plays the guitar or the trumpet. Now the cool thing is I don't even know if he plays the violin or not, right? I don't know. I have no idea. But just by assuming that he can play the violin or not, then I can actually prove that he either plays the guitar or the trumpet. But I don't really know anything about whether or not he plays the violin or not. I just know that he either plays the guitar or the trumpet. So how's that? Is that confusing? So we can actually argue logically from something that you don't even know what other things might happen. Isn't that amazing? Because if he plays the violin, then you know that he has to play the trumpet. But if he does not play the violin, then you know he has to play the guitar. How does that sound? And let me make sure you're following along. So if he can play the violin, which we don't know if he can or not, then this part would be true, right? But if that part's true, then this part's not true. But if this part's not true, he has to be able to do one, either this or this. So he has to be able to do this since he can't, since that part's not true, right? So that proves that he plays the trumpet if he can play the violin. But maybe he doesn't play the violin because we don't really know. So if he doesn't play the violin, then that makes this part false. But if this part is false, and at least we know that either this part is true or this part is true. So if this part's false, then this part has to be true. So that means that he plays the guitar. So we know that he either does or doesn't play the violin. So therefore, he either plays the guitar or the trumpet. It's kind of confusing. Let's try to think of one more example of that so it makes even more sense to you, because this is kind of important. So what's another example of that? Can anybody think of two other things that are independent from each other, but you could do one or the other?
PC.
Okay, so PlayStation, Xbox, and what else?
PC.
So you can have a PlayStation. I'll just say have PlayStation. Have PlayStation. Let's say that Bill has a PlayStation or has an Xbox. You don't know which though, right? And now you know one other fact. You know that he either does not have an Xbox or, is it okay if I write the symbol for or? Perfect. So either he does not have an Xbox or he does have a PC, right? PC. So what valid argument could you make from that? So once again, we don't know if he has a PlayStation or not, but let's just, oh, I keep doing the wrong thing on the bottom of this. I keep putting not Q instead of not P. Okay, see, that would be an invalid argument if I did that, so let's fix that. So it says P or Q, right? And then it says not P, so not PlayStation. Or has a PC. So we don't know for sure if Bill has a PlayStation, right? So let's just consider both options. If you don't know something, you have to consider both possibilities. If Bill has a PlayStation, then we know if he has a PlayStation or has an Xbox. We don't know if he has both though. But if he has, so if he already has a PlayStation, then we cannot say for sure whether he has an Xbox, right? Because he doesn't have to have both. If he has a PlayStation, then we don't know for sure if he has an Xbox. So we can't conclude that for sure if he has an Xbox. But if he has a PlayStation though, remember, we know that he either does not have a PlayStation or he has a PC. So if he does have a PlayStation, then you know that he does not have a PlayStation. So if he does not have a PlayStation, then he has to have a PC because we know for sure that he either doesn't have one of these or he does have one of these. Right? So if he does have a PlayStation, then he has to have a PC. So he either has to have a PC if he does have a PlayStation. But what if he doesn't have a PlayStation? If he doesn't have a PlayStation, then we don't know for sure if he has a PC because all we know is he either does not have a PlayStation or he has a PC. So if he does not have a PlayStation, we can't say for sure whether or not. We can't say for sure if he also has a PC or not. But if he does not have a PlayStation though, then we can know about the top part though. If he does not have a PlayStation, then we know that this part's false, but we know this part is true or this part is true. So if this part is false, then this part must be true. So if he does not have a PlayStation, then he must have an Xbox. So in a nutshell, if he has a PlayStation, then he must have a PC. If he does not have a PlayStation, he must have an Xbox. So since he either has a PlayStation or not, he therefore must either have an Xbox or a PC. How's that? Now, we don't know which one's true, right? We don't know whether he has an Xbox or whether he has a PC because we don't know for sure whether he has a PlayStation or not. But he has to have one or the other, right? Because he has to either have a PlayStation or not. So sometimes you can prove things even if you don't know what's exactly true. So that's exciting. Okay, so any questions about those arguments? If not, let's go ahead and work on some practice problems together. Okay, perfect. By the way, let me bring up the book on this other thing. Okay, so let's look at page 93 of the book and example 1.6. I think you're going to enjoy this. Okay, so let me stop sharing right on the screen. And wait. One second. Wait, I forgot how to stop. Just a second. Okay, there we go. All right. Okay, so I'm going to prove an interesting proof to you. Are you ready to have your mind be surprised? Okay, I shouldn't say that. I might be ready to prove an interesting proof to you. So we're going to start with one. So we're going to start with two numbers. First, is it possible, do there exist two numbers such that A equals B? So let's just assume that this is given. Is it possible for two numbers to equal each other? Of course it's possible. So this step of the proof is easy. We can just assume that we are given two numbers that are equal to each other. So this can be true, right? Now, if that's true, let's multiply both sides times A. So if I multiply the left side times A, I'll get A squared. If I multiply the right side times A, I'll get AB. So do you see any error in that? Is there any logical error in that at all? Okay, step 3. By the way, the purpose of this is try to make you lose attention and forget where we started. Most of these steps are actually just busy work, basically, but pay close attention until you can see if there's a mistake. Now, the next step is we're going to subtract B squared from both sides. So if I subtract B squared from both sides, I'll get A squared minus B squared. If I subtract B squared from the right side, I'll get AB minus B squared. Okay, so is that correct? Yeah, that's fine. Fourth step is I'm going to factor. Well, there's nothing wrong with factoring. You can factor the difference of squares. You've learned this in algebra. A squared minus B squared is equal to A minus B times A plus B. If I factor a common factor of B, I'd be left with A minus B. That's easy. So now I'm going to divide both sides by the same factor of, what's the common factor of both sides?
Square.
Hold on, let me draw some lines so you can separate these things. So A minus B, right? If I divide both sides by A minus B, I'll get, hold on just a second. We get A plus B equals B, right? Okay, now, based on my assumption that A equals B, have I specified which numbers I picked for A and B? Have I specified which ones I actually picked? No, so let's just replace A by B in 5. So let's just, since A equals B, that's the initial given condition, I'm going to just replace. So since A equals B, therefore I'm going to take A and substitute it for B. So I'll get B plus B equals B. Is that valid? Okay, then I'm going to get 7, 2B equals B. Now, have I specified which number B and A actually are? No. So is it possible that I can just, like, let's say, assume that A equals 3 and B equals 3? Is that possible? Yeah, sure. So like I could assume it's whatever I wanted to be, but so I'm just going to divide both sides by B now. So if I divide both sides by b, I'll get 2. What will I get? What's the next step? 2 equals 1. So have I really just proven that 2 equals 1? Is it true that 2 equals 1?
No.
No. So where did I make a mistake? 4?
I feel like because a minus b should always equal 0, right? So
Yeah.
divide it by whatever that is, it should always be 0.
Well, but I was just factoring those. So 4 is still true, actually. Like all the way down to line 4, it's still true. Look at the steps I did on the right, though. Or any of the steps on the right not actually valid. Is it always true that you can multiply equation by an a and get a true equation? Yeah, that's true. Is it always true you can subtract a b squared from it? So are there any rules of math that you've learned not to do before? Not to do what? Never do what? When you're working algebra, there's something you're never supposed to do. And we did it in one of these steps. Are you? Think carefully about, okay, you're close to the right answer, not quite at the right answer though. What happened right after step 4? Because you thought about step 4. What happened right after step 4?
Then by a minus b.
Yep, exactly. And that's normally fine, but except what was our given condition though? A equals B. So what is A minus B if A equals B?
0.
Yeah,
Right.
so
Yeah.
so actually since A equals B, that implies if A equals B, then what is A minus B? 0. And so I said I was going to divide by A minus B, which if A minus B is 0, I just divided by 0. That's not possible. So this equation right here actually is not true. What you actually get when you divide by 0, you get undefined because 0 doesn't actually divide into anything. It looks probable, but this equation actually doesn't exist because dividing by 0 doesn't exist. So it isn't true that 2 equals 1. So this is just one example. There's lots of funny tricks you can do if you divide by 0 without making people realize it though. Okay, let's look at page 95, question number 2. Question number 2. All right, perfect. Page 9, sorry, let me write that again. Page 95, question number 2. It says use a direct proof to show that the sum of 2 even integers is even. So an even number plus an even number is supposed to be an even number. That's what we're supposed to say. Now we have to know one little trick to help us do this though. The way to represent an even number is with this formula. First, you have to, in a proof, you have to always say let. Like how God said, let there be light at the beginning so that light could be there. We have to say, let there be 2 integers. And they usually say k for an integer. So we're going to say j and k because we need 2 of them. And jk stands for my first name and middle name, which stands for just kidding. But this time I'm not just kidding though. So let there be 2 integers j and k. If there's 2 integers j and k, then an even number then an even number is of the form two j. Okay, I'm writing this a little bit. I'm writing this a little bit wrong actually, because you can't create something specifically before you actually define what it's for. So we're gonna say let there be an even number 2j and 2k. So let there be two even numbers in the form 2j and 2k for two integers j and k. That's the most frustrating part of the proof, is to properly define it, because you're basically creating things out of thin air. So let there be two even numbers, which are of the form of 2j and 2k for two integers j and k. Why is an even number of the form specifically two times an integer? Why is it even number two times an integer instead of just being an integer?
Namely divisible by two.
Yeah, so if we just said that it's just the integer j, well, the integer itself might be an odd integer. But if we know it's two times an unknown integer, we know for sure that it's an even number. Okay, so we're now supposed to prove that an even number plus an even number is an even number. Okay, so an even number plus an even number is equal to 2j plus 2k, right? Which is, now let's factor out the 2. 2 times j plus k. Now, we don't know if j and k are even or odd. We don't know if j plus k is even or odd, and we don't know whether j is even or odd, and whether k is even or odd. But we do know that j plus k is what? If you take one integer plus another integer, it's always an integer, right? So we know that 2 times j plus k is 2 times an integer. And anytime you take 2 times an integer, you get an even number, right? That's, this part of it is just assumed to be like basic knowledge of arithmetic. So an even number plus an even number is always 2 times some integer plus 2 times some integer. If you factor out the 2's from both of them, you'll get 2 times a bigger integer. But 2 times any integer is makes an even integer. So that's pretty cool. Let me give you a mystery to talk about, and then we finish talking about this next time. So next time is Friday, right? Okay, so I'll give you a mystery to think about. Think about the powers. Think about the powers of numbers. What's 1 squared?
One.
What's 2 squared? What's 3 squared? What's 4 squared? Now there's a mighty strange mystery. I guess it's a mighty mystery that a lot of people have always wondered about. It's extremely mysterious. What's the difference between every square and the next square? Think about that. Why is this true?
Is it 3
It's
plus
3.
ten?
And what's the next difference?
5?
And then what's the next difference? So what do you think the next one's going to be? So what's 16 plus 9? Is that true? So can we actually prove or not whether the difference between every square is always an odd number like that?
No, because it's crazier.
So we'll think next time about trying to see if we can prove that or not. So that's your mystery to think about before next class. So by the way, make sure you look into the PowerPoints and stuff like that, because the PowerPoints are pretty self-explanatory. They're on Moodle, and make sure you're like reading through the book as much as you can and thinking about it. The important thing is to think about all this as much as you can. Yes.
Sorry, 1 second.